short piece on what I'm going to call the manifesto for complex systems. This is to give just a really, hopefully clear, simple framing about what we're talking about here, which ultimately is really modern science. Oh, I'm in the wrong spot, so I'm going to. Okay. All right. So let us talk about things. Let's get on the right object. The usual team. So I'm just going to give a simple definition for complexity. I'll kind of come back to that. And then this one-page manifesto for why this is why all of this makes sense here and now. So big part of it will be just how science has worked and necessarily worked would work if we were actually to be successful. So reductionism, we have to figure out all the small pieces because they're real and they exist. Quarks, maybe, okay, but all right. And then the manifesto. So that is, and the symbol here is the shovel, because ultimately what I want to say here is just get on with it. Do modern science. Don't be stuck in tiny little bracketed disciplines. Even if you are really a specialist, you need to know about other areas. Right, so the word complex is a good word. So made up with folds or weaves, right? So some sense of intricacy. And you know what? I'm happy to sort of look at the etymology of some of these words that we use and feel that we can be at peace with them, right? We don't have to go to something more. They won't be dug up and sort of thrown away later on. They may, but I don't think they need to be. There are previous terms here like cybernetics and so on, which are sort of branches of what we might think of as parts of complex systems. It's not a great term. So I think this is a good word. Systems, these are good terms. So complex systems were solid. There's complicated. This is an old thing that's been talked about many times. And I just want to separate them a little bit. So traditionally a mechanical watch, you could have someone who would understand it completely, could take it apart and repair it. My wife's, one of her grandfathers was a repairman. And it's quite a skill, but it could be all in your head. You could understand it completely. That was true of planes as well. Early on, mechanically, you could kind of have the whole thing in your head. So these we might refer to as complicated. Now they have ultimately become complex as well, in that there are behaviors that we didn't quite, build in, or certainly had no idea might have come out at the end. So we'll get to that as we come back to foundations of complex systems later on in the course. But ultimately, many of our engineered systems, once they're of big enough scale, can also be complex, right? So, and we'll come back to robustness and all these sorts of things later on. So we can make these engineered systems that do one thing, but they're not really adaptable, right? So we get excited about robots that might hit a baseball or clean the floor for us, but we can ask them to try to do some other things like, make the toast, and not so good. Or yeah. All right. So we've been pretty good at engineering systems that do certain things. They're not necessarily then adaptable. I know the robots will come eventually and they'll laugh at this, but yeah. All right, so as I said, engineered systems can certainly become complex. And the big deal we'll have in this is emergence, right? So that there are behaviors, and I know I talked about this probably in the introduction, but there are behaviors and phenomena at the macro scale that aren't in any of the parts. Right, so hurricanes are not inside water molecules. So we can get to that. And power grids, of course, a famous example now, and very problematic, right? Power going out for large populations, previously impossible because we didn't even have power. But once we started to connect things up and we get to continent scales and so on, then these not just emergent good things can happen, but of course these unexpected emergent bad things. And planes have worked like that as well too. So we've seen that a little more recently, where we've had trouble building some of these more sophisticated planes because they aren't really in anyone's head anymore, and some things can go wrong. Okay, so spectacular failures are always in the offing. So you'll hear this phrasing, complex adaptive systems. Now, I'm a simple-minded person from a physics background. I want to understand how things work, so I'm more general in my way of approaching things. So complex systems is fine for me. So fluids, absolutely complex system story. And again, something I'll come back to later in the course, but one of our greatest achievements is understanding fluids, and it's absolutely a micro to macro story. Navier-Stokes equations, crazy success. All right. So here's just a simple definition for complex systems. So distributed system. So, and there are lots of parts involved. Now, lots can be a little funny, and in some cases it can be really just three, right? Because you can get emergent behavior that's not obviously in any of the individuals. Three planets, for example, can give rise to chaotic behavior. So no, I hope what I just said is not a lie. But anyway, so no centralized control, or some limited centralized control. Certainly there can be some, but no dominant centralized control, because then we're away from anything interesting happening. Of course, this is what authoritarian regimes would like, or people who want to dominate families or institutions or whatever it is, or their high school group, right? Simplifies the behavior. Leviathan. So more is different, and this is a profound piece by Anderson. Let me see if I can make that all still work. Yes, this will pop up. Another example of this. Here it is. Not here. Okay, we'll go back. Let's open another place. But this is the idea that as you go up through levels of systems, and starting with quarks, for example, if you like, or atoms and so on, you get to behaviors that are not at all evident in the lower forms, right? So we don't very easily predict a platypus if we have a box of quarks on the table. So more is different. So the idea is, so more things, you get to qualitatively different behavior. So there's qualitative, quantitative, qualitatively different behavior, right? A hurricane is this swelling is a different thing. It's not, can't look at an atom and see it. So there are other pieces, and that's all I want to say, right? So they could be networked, but just they're interrelated, they're connected in some way, and there's going to be some emergent behavior. And our ability to describe that emergent behavior, let me go back to that and just say, is, that's this great challenge of science. And so there are some fields, again, like fluids, where we've been able to write down the Navier-Stokes equations and explain a lot of fluid behavior. However, something like turbulence, where the equations break down, we get into trouble. And my thinking there is becomes more in the realm of algorithmic behavior. So evolution is full of algorithmic behavior. Social phenomena full of algorithmic behavior. The economy, and we'll come back to that when we talk about stories. So, okay. There can be this kind of explicit nonlinear relationships, that can be kind of come out of the fact that there's some network connection between individuals, so it might not be manifested at that level, but there could be explicit, little feedback loops, right? These are things that people have thought about for a long time now. Open or driven, so that means that there's energy coming into the system from the outside and being taken out. These are all possible parts, but I'm not saying they're necessary. Memory, most systems that we're worried about and interested in, there's a lot of memory. I mean, the Earth has memory because it's still here from 1 billionth of a second ago. So there's just memory of the state you're in, and then there's memory of, back in time, like, our memories. Things get a little timey-wimey for us. And we have work on that, which I might talk about later. Modularity, and so this actually does seem to be something that's observed over and over with real systems, particularly evolutionary created ones. And engineering ones can work in that way too. But there's some modularity to it. Okay, so even software, for example, right? There's sort of some core pieces that are used over and over again, and they become parts of bigger and bigger systems. So a huge amount of work has gone into, let me see, I don't have my gloves on, that's a problem. A huge amount of work has gone into taking enormous networks, right? So enormous amounts of data where we have lots of little individuals that interacting with other individuals. We have all of that, and it's too much to put in our own minds. Hundreds of millions of nodes with, maybe 10 to 100 interactions per node with all the other nodes. What does that look like, right? You can't just go splotch and put it on the wall. People do that, but it's not great. So a lot of effort there to figure these things out, and we'll talk about that. If you've worked with networks, I'm sure you've come across that. Community detection or is one framing or structure detection. Yep. And I touched on this before, but the mechanisms involved in complex systems go from being purely physical, right? So there's the astrophysics. We have all this very interesting, beautiful structure, right? Galaxies and so on. And there are all sorts of things about information being at the bottom of all this. But this is sort of a raw physics story. Gravity, it's a big deal. Again, something we'll touch on later on. But I would think as we go up through these scales, the emergence of life, the emergence of interactions between species and organisms and so on, and ecosystems, then what I'll call socio-technical phenomena, people plus information systems, computer systems, connecting systems. More and more we see algorithms come along. Right? Language is full of algorithmic behavior, social interactions, algorithmic behavior, economic, the way organisms interact with each other and make decisions. Pratchett is full of little algorithms in his head about eating food, watching things that he might want to eat, thinking about how to eat them. So, I mean, maybe it's a simple set, but they're interesting. So, complex systems. There are some classic ones, right? So ant colonies are classic ones. Cells, the ways other kinds of social insects work, ecosystems. We've in all these different fields, we've struggled with thinking about them, measuring them well. Again, a big point we'll come back to. Measurement is the foundation of science. Measuring them well, trying to understand why they don't fall apart in the first place, right? That's kind of extraordinary, how they've evolved to be where they are. We've certainly gotten to systems that are, it's kind of amazing they got to that place. But we were able to trace back through evolutionary history, the origins of eyes, the origins of ants or whatever it is, and so these are interesting problems. Forests, super interesting developments there in the last, I think, 20 years of trees being connected to each other through root systems and through fungal systems that are little highways for nutrients and so on. So there's a lot more communication in forests than we've seen before. So complex systems are everywhere. And if we think about right now with the pandemic, this involves biology, right, with viruses, the actual virus itself. There's the human behavior on top. There's all the technological stuff in terms of how we move around, the achievements we've made with flight and so on. So that has connected us. Then there's the socio-technical connection of everyone talking online and sharing news and so on, and we end up with people behaving in very different ways. And well, if the virus was a could think it'd be sort of steepling its fingers with some of the decisions we've made, for sure. But to try to respond to this and to do it well, you need to really be able to think about systems. You need to think about, what if I put this policy in place, we put this policy in place, how do we do it well? How do we help people respond in ways that save each other? Because this is something where the individual narrative fails. It's very much a system story. And all these fields, and I like to think about fields going from data scarce to data rich. This is just a natural progression of science. physics was like this, right? You could look at the stars, but we didn't have telescopes. Then we got telescopes, and then we got arrays of telescopes. So in about 2000, astrophysics changes from being this, sitting out somewhere, maybe in Hawaii, it's all very nice, or on top of a mountain, looking and hoping there are no clouds, getting enough measurements, to this more distributed thing where now it's a lot more computational work and so on. So data scarce to data rich, and that changes. It doesn't change necessarily the fundamental questions you may have asked. You still want to ask those questions, but you'll be able to probably think about other questions as well. So it's just a natural progression. All right. This I'm just going to throw up here, and you could dive into it if you want. But it's an interesting little interesting attempt to trace the history of people who've been thinking about complex systems. So there's some straight up framings back here: system science, Bateson from ecology, Margaret Mead, Rappaport was very famous for tit for tat in the prisoner's dilemma game. Newton gets thrown in there as well because of dynamical systems is enormous. Wiener, very, very famous character. Anyway, so this all, there's just a lot going on here. I want to highlight, if I can, where is she? Should be in here somewhere. Juniper Lovato is kind of right in the middle there, yeah, who is listed here at being at the Santa Fe Institute, but is in fact here at UVM, is the Director of Outreach and Education for the Complex Systems Center, and is also now a PhD student, so it's really exciting. Anyway, she's been a global leader in the education part of complex systems. All right, so that's this is a difficult thing to kind of put together, but hard work, right?